Hey, this is Professor Turner with Purdue Polytechnic, and you're watching the next video lecture for ECET 364 Fundamentals of Electromagnetics. Today we're going to talk about mathematical techniques that are used to describe the electromagnetic wave as it propagates through a medium such as free space or as it propagates through a waveguide. And by waveguide, I mean any material designed to carry an electromagnetic wave. So this might be a wire, coax cable, antenna, any sort of waveguide. So we've got two learning objectives that we're going to cover in the video today. The first is that we're going to use the cosine function to describe the traveling wave. And the purpose of this is that when we describe EM waves in terms of the cosine function, we can then begin to mathematically analyze them using RF circuit analysis techniques. So we're going to review basic wave propagation in terms of the cosine function and the associated parameters. And then the second, instead of describing things in just in terms of the cosine function, we're going to use that old technique introduced to you in previous classes called the phasor notation. And we're going to use phasor notation to represent time harmonic signals, in this case, applying them to something called a traveling wave. So cosines and phasors, big picture for what we're going to be doing today. So I've got an image here just to remind me to play this video. Oops, there we go. And what this video is a image of an electromagnetic wave as it propagates through space. You know, a little cartoon, basically. At the far left here, we've got some sort of point source of radiation. This could be a charged particle that's being moved for some reason, or maybe a better example for electrical engineers is that this is a AC voltage source connected to an antenna, and it's broadcasting a fixed frequency. But the point is that it's just something that's creating electromagnetic radiation. You can see at this point here that both an electric field, which is indicated here in the red ink or red lines, and a magnetic field are, which is in the blue lines, both of those are being established simultaneously. At any point in space and time, the strength of the field is given by the size of these lines. Kind of the size of the lines are drawn on the picture. The bigger the line is, that's just indicating that the stronger the field is at that point in time and in that space. So let's look at the origin here. We can see what's happening is that this electric field is increasing up to a maximum, decreasing back down to zero, going the opposite direction, and oscillating back and forth. So the electric field strength just at this one point in space is going up, going down, going up, kind of at that point of the arrow right there. At the same time that the electric field is going up and down, the magnetic field is going left, right, left, right. And the increase in peak is occurring at the same time in the electric field as it is in the magnetic field. And so when we describe this using technical language, we say that this behavior is synchronized oscillation of electric and magnetic field. That's what's happening there. So you'll notice, I think you'll recognize these shapes, both the E field and the B field are sinusoidal shapes, meaning that their strength at any point in space is going to vary as described by the cosine function, which we've used in many classes before, so I'm sure you're familiar with that. The rate at which the field oscillates, so the rate at which two peaks occur, there we go, there's two, that is called the frequency of the wave, and it's measured in hertz. Basically, you can think of this as how fast two peaks will occur in time. Another way to think of this is the amount of time that it takes for two peaks to appear, which is the period, t, measured in seconds. And frequency and period are inversely related, and by f equals 1 over t, or t equals 1 over f. These are relationships that you're used to seeing in other classes. You also notice that, as I pointed out earlier, the peaks occur in phase. meaning that the peaks and valleys in both the cosine waves occur at the same time, and that there's no phase shift between the E field and the B field. So that talks a little bit about the frequency and the phase. Now notice that it appears, if you look at this picture, it appears like if we were to pick a point like here, that the wave is moving from left to right across the screen. What's actually happening there is that the EM wave is carrying energy away from the source. It's kind of moving along in this direction. And as it's traveling, it's imprinting an E and B field into space as it travels. Since the wave is moving through space, the measurement from one crest to the next crest is a physical distance. It's called the wavelength of the wave, and it's given lambda is its symbol. You can see here it's illustrated as the physical distance between those two peaks measured in meters. If I were to plot a single point and calculate the speed at which it's moving across the screen, that's the propagation velocity, mu sub p, and that, since it's a speed, is measured, or it's a velocity, it's measured in meters per second. So I'll just summarize those a little bit here. If I were to measure the physical distance between two peaks, that's lambda, wavelength. The rate at which it moves from right to left is mu sub p, and that's velocity, propagation velocity. Finally, if I were to pick a point and then count how fast waves past that point, that's the frequency. And the relationships for the electromagnetic wave, as we know, are mu sub p is equal to wavelength times frequency, or since period is equal to 1 over frequency, we can make the substitution that propagation velocity of the electromagnetic wave is equal to wavelength divided by period. That's in meters, period is in seconds, so you get your units of meters per second there. So this is showing a electromagnetic wave moving from the left-hand side of the screen to the right-hand side of the screen. In reality, electromagnetic waves are typically three-dimensional waves. They propagate through a volume. They cause a disturbance in the z-axis. They cause a disturbance in the x-axis. And these waves don't have to be linear like shown here. They can be plane waves, meaning the electric field front propagates as a plane, which is kind of the drawing I tend to use a lot. So you could see this as a wave front moving just in that direction. Or they could actually propagate out spherically, which is actually very common today. So for the rest of today, we're just going to be dealing with one-dimensional waves, meaning that the displacement or the disturbance that the field causes is just going to be a function of two variables, time and a space variable. So we're going to investigate that in more detail here shortly.